Welcome back. In the previous video, we took a look at how the different angles of systems monitoring comes together for understanding how healthy a machine learning system is. And we mentioned briefly about a couple of tools, specifically Prometheus and Grafana. Together, they actually constitute what's called as the modern observability stack. In practice, the stack is actually much more than just these two tools. We'll take a look at a couple of specific extensions of those tools as well. And in the hands-on part, we will combine a couple of them together. We might use some components of GCP as well. But the interesting angle here is that the stack is comprised of open source software and is actually quite portable, adaptable, flexible, and powerful. Can be used in a variety of different circumstances, including for deep learning applications, LLMs, etc. So it's important that we know about this. That's why we're going to spend some time understanding what the observability stack looks like. So let's dive in. So what observability focuses on is not just monitoring, which is what we did in the first video, but it's also interested in peering into the system, right? And trying to make sense of some of the symptoms that are coming from the system. So the key is that it doesn't know anything special about your system, except for the outputs that the system itself is producing. So let's say, for instance, it's a machine learning model running on a Kubernetes cluster. Whatever the model chooses to output as matrices, as logs, coupled with what the Kubernetes cluster is able to tell about the execution environment, including CPU, memory, etc., those together constitute the information. To make sense of this information, observability practices put like 3 or 4 things together and correlate and try to understand what sequence of activities resulted in this combination behavior. So that's observability. So the analogy here is if you've used cars in any form, like maybe your family has a car or you've been in a taxi, you'll get to see that the dashboard of the car has a whole bunch of different lights or sensors that glow, and each with slightly different color. So the car, let's say, breaks down for some reason. Then as a mechanic, obviously the mechanic would know the inner details about what's happening. But as a driver, you're just a user of a car. You're not really an expert. So then you rely on the indicators, like the ones on the car dashboard, like to understand what is happening. So if the fuel is really low or it's empty, then the fuel gauge is empty. The oil needs to change, then the oil indicator comes up, etc., etc. If the car is too heated, then there's some other sensor. So then these sensors become the biomedia for you to understand why the car is actually broken down. It might still not give you the clue as to the exact reason why the car broke down, but it might give you broad indications of what might be happening. So that's actually observability in action. That's one of the earliest examples of observability in the real world. So observability then, if you do it well, it can actually really help you answer questions like, is the system working as expected? And more importantly, if not, what went wrong? Where did it go wrong? And potentially, why did it go wrong? So it's in a lot of ways like allopathic medical treatment. It's symptomatic treatment. It's going to work in most of the cases which are common, but it's not the same thing as root cause identification, which means the cure for what you're trying to do or the actions that you want to take, the response you want to take, depends obviously on the root cause that's been identified. And therefore, if you're not able to find the root cause accurately, then you're going to end up having a cure that is either a patchwork or potentially not a cure at all. So observability is going to provide you a lot of automation, but please don't get misled by that. That automation is not a replacement for human intelligence, which is critically required to make deductions so that you can arrive at the root cause more correctly. So the reason I'm mentioning this is that there are many tools which are proprietary in the observability stack, particularly as it pertains to data observability, AI observability, LLM observability, which claim to actually have innate intelligence about what is actually happening. At the end of the day, what they do is correlation, right? And we all know the classic adage from machine learning education, which is correlation is not causation. And if correlation is not causation, you definitely cannot pinpoint the root cause of a problem, right? And therefore, arriving at a cure becomes equally challenging. Keep that in mind as you go through the usage of these tools. What data sets do you need for observability to make full sense of what is happening and give you the best kind of outcomes? There are three sets of data, three data elements. The first is matrices, as many matrices as you can get about the system execution. We saw a bit of it in the systems monitoring, latency and things like that. Basically, it's numeric data about system performance. Prometheus becomes the natural vehicle for us to collect these system matrices. But then you also need a way to emit these matrices from the application. That's where something like OpenTelemetry or StatsD become useful. Then the second type of data element is logs. Logs provide verbal cues. Logs provide developer-informed cues into what's happening, right? So they become the detailed records of certain types of events or actions. And then you use a log collection mechanism like FluentD or Loki to collect these information or collect these logs and then stage it in a central place, and you can use it for correlating against the matrices. The third is traces. Traces is actually a very interesting concept. As the name suggests, it's a way to trace a specific request that came from the user as it wound its way through the backend systems and then eventually returned to the user with a response. The trace actually goes through multiple different steps or multiple different services. To be able to trace all of those different services that need to execute for one trace, for one request to come back successfully, is what traces is about. For a modern software system, which has multiple different containers, multiple different microservices, each having its own API protocols, and then having handoffs between them, it's very important that you understand how a trace can be created, because otherwise you might end up getting lost in the logs of each of those microservices. So think about it. Each microservice is then emitting matrices and logs and things like that. And there could be tons and tons of information. But to be able to get an understanding of what happens to one request, you need to stitch a whole bunch of these logs from different services together. And that could be problematic. So without traces, this is an unwieldy exercise. So request flow across services, especially microservices, is what traces is about. Again, OpenTelemetry plays a critical role. Jaeger is another example of a tool that can be used here. So given that, let's start taking a look at one of the first and most important tools in the modern observability stack, OpenTelemetry. It's an open source. It's an open source standard for generating and exporting observability data, specifically matrices and traces. It's supported by the Cloud Native Compute Foundation, or CNCF, which is a consortium body of a whole bunch of technology providers which are adhering to the cloud native principles. It works across languages and platforms: Python, Node.js, Java, etc., etc. Doesn't matter. Golang, and then it's compatible with the rest of the stack, which we're going to look at, Prometheus, etc. There are also third-party proprietary tools which are in the space of observability. Datadog is one such example that's very useful for data observability. Public cloud vendors themselves provide a lot of stack information, a lot of stack technologies for observability. So we're going to take a look at some of them in the hands-on portion of this week's lecture. So what's a core component of OpenTelemetry? It's the SDK. The SDK allows us to plug and play a lot of out-of-the-box functionality that OpenTelemetry provides in various languages. So you have SDKs for Python, for Java, like I said. So in the hands-on portion, we're going to use OpenTelemetry's SDK for Fast API, or Python, basically. Obviously, OpenTelemetry also has APIs, so that's great. So you can use these for, embedding code in your app and ensuring that the telemetry of your app is recorded correctly. It's got a collector which receives information from these SDKs or the usage of the SDKs, processes some of it, and then sends it or exports the data. And then it's got exporters. The exporters play a role to send data which is being collected by the collector to backend systems. Prometheus is a good example, or GCP, for instance. So the way you would use it is, you would embed this kind of code within your app, like let's say the Fast API container that we developed so far. OpenTelemetry, import matrices, and then Prometheus metrics exporter, and then you start exporting to the exporter a bunch of like matrices or meters that you compute. Then Prometheus in turn will scrape the metrics endpoint and ensure that it's always getting the latest information about that particular app. So that's one way of going about it. We'll see another example of it in the hands-on portion. Prometheus itself is the metrics collection software. Again, open source. It collects and stores all these matrices in what's called as a time series database. A time series database is just a specialized database that is optimized for storing time series data. What is time series data? It's basically an event time that gets recorded with every single metric. That's all it is, right? So time series data turns out to be a very naturally occurring data set for these kinds of observability information. So it's great for monitoring applications, infrastructure, services, because the moment you have time attached to these elements, then you start to think about trending, about alerting, about stale information, about latest information, etc., etc. So how Prometheus works is it scrapes matrices from endpoints that expose them. Usually apps need to do this explicitly. So you create what's called as a metrics endpoint, and then you make these matrices available. Always you're computing matrices locally within the app, like for instance, latency, number of requests that have been received, total requests processed successfully, how many of them failed, etc., etc. And then as and when you expose them, you get Prometheus to come and take a look at collecting this information and storing it in its time series database. Metrics are typically numeric. This is not useful for log information. That's separate. I'll get to it in a minute. So what's the use case, the most important use case from Prometheus? Like I said again, it's symptoms that it's recording across the board with respect to numerical values related to the system on which the app is running. So it's in effect designed to be that particular system that you go to when an outage occurs in your machine learning application. It's like the black box for your machine learning production systems. Not just machine learning, even for modern software, I should say. So the way the Prometheus server is deployed is it's deployed in a way that's standalone. It's not connected to the rest of the network infrastructure because everything happens using HTTP protocol. So it's RESTful in that sense. So therefore, even if the rest of the network goes down, or there is a cybersecurity attack, or there is a performance issue with a specific node, as a result of which the node is not accessible anymore, etc., etc., or there's a denial of service attack, which brings down the core endpoints that are servicing the business functionality. In all of those scenarios, Prometheus will still keep running because it's running behind the scenes on a separate network. But what it's not meant for is to track consumption to the T. By that I mean, if you're looking to build a billing system where you're looking to invoice certain consumers based on the number of service calls they make, then for that kind of a design pattern, you would need what's called as 100% accurate logging of every single consumption request that's coming. Prometheus is not good for that. It's more meant for where you can tolerate a bit of data loss, where it's doing a bit of aggregation. It might not be storing the raw information all the time. Then Prometheus is actually a good example of a technology that can be used under those circumstances. The last technology that's interesting in the modern observability stack is Grafana. This is meant to be the de facto tool that's used for visualization and dashboarding. So OpenTelemetry allows you to pump data out from your apps Prometheus allowed you to collect all this information in time series databases and then did aggregates or alerting on top of that. Grafana allows you to now visualize these matrices, and not just visualize, but also do dashboarding, do various other things. So it's, together it's very powerful with both of these technologies. So some of the features that Grafana has, real-time graphs, various UI elements pertaining to data visualization. Then it also supports queries on top of this data using a specific language called as PromQL. It's like SQL, but built for time series databases by Prometheus. Then it can also connect to multiple data sources. It doesn't really compulsorily require Prometheus as a backend. You can make Grafana connect to Elasticsearch backend or a Loki backend, etc., etc. So here's how the sample Grafana dashboard looks like. You're going to get a whole bunch of useful, plots and things like that. And then you can obviously add your own elements to it on top of it, which means you can plot your own matrices, you can have your own tracking, you can have your own alerting, incident management, all of that riding on top of the base Grafana packages. Now, Grafana is also a fully hosted cloud solution by the Grafana company itself, but that's a paid offering. So if you just want to stick to open source, then you will have to also figure out where to host these services yourself. So how does it all come together? So the architecture looks like this. It looks fairly busy as a slide, so let's just walk through it. The bottom left, you see these jobs or exporters. Effectively, these are the apps. The apps provide endpoints which are exposing these matrices, or they use OpenTelemetry and are publishing matrices to specific, endpoints. Then you could also have short-lived jobs. You see this on the top left. These are, not long-running. This is not like a permanently running machine learning prediction API. But these short-lived jobs are pushing matrices as and when they finish. They compute these final summaries and then they push those matrices. In either case, there is a push gateway that is part of the Prometheus infrastructure, which receives those matrices and then pushes them into the Prometheus server database itself. But alternatively, if you've got Prometheus to come and scrape the matrices endpoint, then it does a pull directly into the backend. So either which way, Prometheus is able to deal with both push as well as pull types of matrices. Then Prometheus is further able to also discover services that have been hosted in your environment, like for instance, containers on Kubernetes, in which case those targets can be discovered. And then these are open source again. Kubernetes is open source. So Prometheus has standard ways in which it collects that information from Kubernetes exposed endpoints. So therefore, you don't need any special, jerry rigging to happen there. It just happens naturally that Prometheus is able to bring that data in as well. So what does Prometheus do within once it collects all this information? It has the fundamental storage area as the time series database or TSDB, which in turn uses dedicated nodes or physical infrastructure on which disks are present, and then the time series database gets written to it. But before it reaches the time series database, there are memory layers which are called as retrieval, which are temporarily storing this data in memory. The observation here is that for most users of these kinds of metrics data, the most recent data is the one that's the most relevant or the most accessed, right? Like for instance, if you want to know about the health of a machine, it's important to know the health as of now, not equally as important to know the health as of 1 week ago. So therefore, the optimizing that happens here is with respect to the most recent data or the most fresh data, and that gets stored in memory and used for immediate retrieval or immediate visualization. And the older data sets get persisted on the disk. So that's the Prometheus server. Then the Prometheus platform also has its own web UI that's meant for issuing PromQL queries to get very specific types of aggregated outputs. But then more commonly, you're going to use Grafana. So Grafana is able to use PromQL as well, hit the time series database using HTTP requests, and then get back matrices, and then Grafana plots them for you, which is very interactive. Obviously, you could take this database and then have all of this data exported out through APIs, and in which case API clients are also going to be using the same PromQL protocols. Additionally, Prometheus can also give you alerts. So these are push-based alerts because the time series database is actually always calculating these aggregates and patterns. And then the alerts get pushed to the alert manager. And then Prometheus alerting can be integrated with downstream channels. It could be Slack, it could be email, it could be like a chatbot. It could be, tools like PagerDuty, etc., etc. So this is the observability architecture, which is heavily centered around data that's getting produced by your apps and getting collected in a stack like Prometheus with Grafana for the UI and OpenTelemetry for publishing from the app as well. So let's summarize what the stack is and how you would use it. And in fact, what we're going to go as a homework for this week is, while I'll show you an example of how this stack gets used in a dummy machine learning model application, you're going to build this stack on top of the homework pipeline that you've been working on iteratively every week so far. So your app uses the OpenTelemetry SDK to define and record matrices that are of interest. These matrices are exposed at a metrics/metrics endpoint, usually using Prometheus's custom exposition format. Then Prometheus goes and scrapes this information periodically and then stores this information or stores these matrices in its database. And then Grafana gets used for monitoring this. So the same set of functionalities that we just saw with the modern observability stack is also available within GCP. So these then become the GCP native tools that are available to you. And the reason this is something we're talking about is because we use GCP for our assignments, for the hands-on portion of the labs. But a very similar set of tools exist within other public cloud vendors as well. So this is not to say that these tools are exclusive or these functionalities are exclusive. Functionalities are not. Anyway, for GCP native tools that correspond to what we've just saw, let's take a look one by one. GCP has something called as cloud monitoring that provides a unified view of matrices, logs, and provides dashboards for even things like Kubernetes engine workloads, GKE workloads. Cloud logging is the logging service which is centralized. It collects logged information from all parts of the GCP stack and centralizes it for you so that it's easy for you to come and take a look and query and search and do all kinds of things. Cloud Trace is meant for tracing specific requests across different services. It cannot obviously function on its own without corresponding instrumentation on the source application. And we'll see with the hands-on example. Cloud Profiler is meant for looking at resource utilization like CPU memory and seeing what is used optimally at what point in time. And Cloud Load Balancer monitoring is specific to when we use a load balancer, which we do use, like the Kubernetes example that we saw from the previous week ended with the load balancer as an example. So being able to look at load balancing activities, the latency associated with it, the backend errors, the traffic volumes, the routing to the different pods of the Kubernetes cluster, all of that is part and parcel of load balancer monitoring. So let's dive deeper into this as part of the hands-on session later in this week's lectures. Examples of alerts that you can set up in GCP, just like the tools themselves, you can actually now set up alerts. You don't need Prometheus for alert management per se if you're going to use GCP directly. You can set up alerts on CPU usage of a specific pod of a machine or a node, memory usage, API latency on the 95th percentile or 99th percentile, that's up to you. Request error rates, be alerted on pod crashes, restarts, etc. And then, failures of the liveness checks or the readiness checks. And for each of these alert types, we can also configure specific behavioral patterns. Like for instance, I don't want to be alerted for every time a liveness check fails. It could be just a blip. But if it fails continuously twice or thrice within a span of 3 checks, then something is wrong. I want to do something about it. So you can define those kinds of fine-grained matrices as well as you go about using these GCP alerts. So let's put it all together with respect to what typically occurs when MLOps problem statements come about. So there are various scenarios which are common. Under each of these scenarios, what can be used for debugging, troubleshooting, root causing is what we're going to talk about now. So let's say, for instance, your machine learning model API is suddenly slowing down, right? And that's the first scenario that you're interested in. So in these kinds of scenarios, the way you would be able to root cause what's happening is by looking at latency matrices over a period of time, so that you start to understand at what point the latency started to become lesser and less. More and more. Response times became more and more. Right? So that's scenario number 1. Scenario number 2, model invocations are failing with 5xx response codes. So remember that all of the API requests are going over HTTP protocol. And as per the protocol, every single request will be met with a response, and the response will have a response code attached to it. So if the response is successful, then the response code is 200, and usually that goes with a message of what's called as OK. But if the response is not successfully met, for various reasons, could be the server going down, blah, 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 then the corresponding response codes get sent out. So the 5xx response code typically corresponds to aspects about the resources, etc., which require further debugging. So here, what comes in handy for root causing is the logs and the matrices to tell you which part of the system is actually failing. Then the third kind of scenario that's very common is model response becomes inconsistent. Like for instance, one of the examples that we saw from last week's hands-on session was the same model. If I invoke with different input data sets, it should give me different classes, right? Because it's a multi-class classifier. The iris problem statement was a 3-class classifier. But if it kept giving me the same class all the time, then something is wrong. By the system logic itself, nothing is wrong because it's successfully giving a response. But the semantic meaning of that response is meaningless, right? Or it's not consistent meaning because it keeps giving me the same class irrespective of the input data distribution. So that model response becoming inconsistent is something that you can detect or root cause by looking at the data drift. And we're going to see like a more detailed example of this in week 9. Or resource stress, right? That could be a reason as well, because there are not enough resources, so default responses are going out. Then service crashes can happen every now and then. In fact, as you go through the hands-on exercise in this week's lecture, it's quite likely that you might see a crash or two because something is not configured correctly. So in which case, how do you debug that? You can either debug that as a data problem, in which case you can look at the traces, or you can debug that as a systems problem, in which case you look at the logs. Either which way, that will give you root cause information, which is quite useful for you to understand what's happening. Or the model invocations are failing with 400 class response codes. So here, the like 422 specifically, here it refers to the fact that the server was not able to process the input data, right? Other 4xx codes indicate service unavailability, things like that. But 422 specifically is about input data not meeting the expectation. So therefore, it's not parsable. And because it's not parsable, the server crashes or there's an exception. So in these kinds of cases, the traces information might provide you information about the data itself that's getting sent out as a payload. And then along with the logs, you can take a look at which data is getting scored and what is of bad quality. So in general, you want to be able to answer questions like, why is my machine learning model slow? Is it because the CPU is not available, or is it because the data is not good quality, or is it because system availability is a problem, or there are network issues, etc. So to be able to root cause across a bunch of these different types of problems, the observability data is very helpful, and the tools that we spoke about so far play a crucial role in assembling all this information for you to take a final call. So with that, we will pause. We will come back and take a look at what are the sets of responses that you can take based on the observability understanding that you've built up so far.